So for a body of knowledge titled Artificial Intelligence Methods for Security and Cybersecurity Systems. There's actually 5 research threads to get through and some contributions and conclusions with some further work. The problem and motivation was to address civilian platform protection. Now, although military systems do have equipment and processors and data for programming equipment, they're not accessible to the civil domain. So the approach for this, or the motivation for this research was to have a civilian equivalent which was based on artificial intelligence. The approach, therefore, was also to use a Neuro-symbolic AI theme to this research, where it would be part expert system and part neural method, where the expert system would have the advantages of being provable and understandable and reviewable, and the neuron method would be used to produce new rules that could be reviewed, but would have a machine learning content to it, so that we'd have a learning and reviewable safety critical system. That was the approach and motivation. Department of Defense has other approaches to this. They don't actually discuss the actual approaches that they use, but they are trying to synthesize countermeasures from stimulus of spectrum radio signals, and or they're trying to adapt radar countermeasures. It's also an area I've been involved in the past with countermeasure languages and reactive and adaptive countermeasures. But they're all from the military domain rather than the civil domain. From the Neuro-symbolic AI is a rather newish area, and the approach that we've tried to take on this is to combine an expert system derived approach and a neuron derived approach from rule extraction, although we term it formula extraction. For the neural networks to be trusted, they need to be repeatable and deterministic and have some value for a dependable system. And part of the problem there would be the initialization state. HE and Xavier are the kind of regarded as the state of the art of general forms of initialization using random numbers. There are other forms that select from those or use those as a start case, or do some kind of processing of the data set. But these are coupled to a particular data set, and it's not the approach that we're using here. So anyway, the baseline effect is HE and Xavier. So chapter 4 looks at a threat analysis method or methodology that's applicable to the civilian domain, which is not based on prior knowledge and is based more on testing the data, learning something of the data, providing set mappings in order towards countermeasure selection. And this kind of format is a format which has been assessed by the MOD to be releasable to the civilian area. So this research also provides a civilian accessible threat analysis method. So as part of the Neuro-symbolic AI, the Neuro expert system method sort of modified an expert system and virtualized nodes and structured more like a neural network. It also provided a Bayesian network within it to be able to perfect answers and to a better value based on all of the confidences. And this is sort of the forward chaining sort of element and is humanly reviewable. The expert system, though, is unable to learn, so the formula extraction method is a neuron-based a neural network-based approach, and what it does is adds an extra data dimension into the inputs as a new weight dimension, and we can imagine this that each weight has a activation strength with a number of weights in them. So we can imagine that if we had an image, we would have our width, we'd have our height, and we'd have our depth of our colors, and within the color depths we would also have a fourth dimension array, which is actually our activation strength. The advantage of this approach is that it enables comparisons between each of the inputs to deduce the numerical equivalence or relationship between each of the inputs, and therefore it allows us to be able to deduce a formula which represents the relationship between them, and therefore is a formula extraction rather than a rule extraction. The repeatable determinism work, which was on the initialization state, was initially on dense layers, and it would provide an equivalent performance, but it also had the advantage of structuring the weights after learning, which would be an advantage for rule extraction, as all of the weights are now adjacent, so they are easier to generalize. The work was furthered into convolutional layers, and it was able to achieve a superior accuracy with faster or earlier learning, and it was able to produce the same results, better results in both black and white and color images. It was also subjected to FSGM as an approach to test dissimilar data sets in transferred learning, and it appeared that with greater dissimilarity it was able to retain more of the original learning than the random form was able to do with the same dissimilarities. Chapter 8 took the synthetic dataset creator and created a synthetic dataset creator with a programming language, a markup language for emitter languages to describe images, and subjected it to 14 civil marine boat radars and got 99.8 accuracy when subjected to image classification. This is a very high level of disambiguation between a generally acknowledged data set of civil marine radars, which are generally regarded as ambiguous. This was also with an idea that in order to combat the data problem, if a civilian form recognized genuine civil emitters with a high degree of confidence, then deviations from that could be military things and might cause an alarm. So this was kind of turning the data problem around from the military to the civil idea of, instead of having very detailed and secure data, having very reliable recognition of civil emitters. So the contributions actually were that the non-random initializations was repeatable and deterministic while being decoupled from the data set. Dense layers had more structure after learning, and convolutional layers had earlier learning with higher accuracy. The synthetic data sets had lower ambiguity, and they provide a image classification sort of standard that can be used for creating a high level of accuracy, reliability in recognizing a radar mode and set coupling, and it was using a high fidelity of dimensionality in the physics propagation and dataset creation synthetic dataset generator. Those inevitably created new datasets which are now accessible to the civil domain. The algebraic expert system with the neuron model was able to provide a common rule algebraic representation with computational graphs and virtualized nodes, and had a structure closer to a neural network, but it had the advantage of having confidences based on Bayesians, and actually improved its estimate based on those. For a learning method for that, in order to create the rule, is the formula extraction method, which is a numerical discrimination of a neural network to algebra, and that still is using this fourth dimension for weight array to be able to deduce relationships between different inputs. It's still earlier work in that, there's still more work, but what that method does seem to do is simplify the representation that is within the neural network by exposing this fourth dimension, and doesn't require so much depth, so there could be less vanishing gradients as well with that. And then of course we have the civilian accessible threat analysis framework, of which those two previous techniques for neurosymbolic AI could be heavily utilized within those. So there were some papers published. So it turns out that there's quite a big potential for cyber electromagnetic and AI activities to be combined And it looks like that the neurosymbolic AI using an algebraic neural expert system and formula extraction may have some ability to perform a role within this. And it looks like that those things may well have an ability to work well, but based on the basis that repeatable determinism also makes them more palatable for dependable systems. Also, the data sets can be synthesized to enable further research in all of these areas where there is neuron methods involved. And that idea of turning the data around as well helps the classification of data to be used. Future work, the non-random initialization has aliasing problems which will need to be looked at to make them further optimal and to create more filters on offer within those approach. The formula extraction and condensed network may look at more complex expressions in those relationships, and further condensed layers form for over deeper networks is an area of interest, and to whether deep is still required or is required as much, and what the effect on vanishing gradients could be, or reducing vanishing gradients. And in image classification, I think we'd want to look at the impact of the FSGM attack and resilience to it, but we'd also want to look at de-interleaving using segmentation or object detection, and further broadband approaches for congested spectrum with a further 4/4 dimension of the spectra. Further data augmentation might be considered in the data sets already provided, etc. The neurosymbolic AI functions to the weight array is an interesting area, and what we would want to be able to do is function extraction as well as formula extraction. And with the threat analysis, we'd look further at the set mappings to establish missing parts of the kill chain and how they would affect. So we're not just looking at the data we've seen, but the data we haven't seen. And lastly, for countermeasures generalization, we could be looking at some approaches to be able to optimize the countermeasures, perhaps through adversarial or GAN approaches. Okay. Thank you for listening.